Welcome to today's webinar, The Return on Investment with Vitech Software, including Core and Genesis. My name is Katie, Communications Manager at Vitech, and I will be your host during today's webinar presented by Zane Scott. Zane is our Vice President of our Professional Services and Training Organization. For the past 25 years, he has built a skill set which enables him to provide insight and guidance to individuals and companies as they improve organizational processes and methodologies across their organizations. He has also taught systems engineering methodology in the practical process context in a variety of settings. Zane has a BA in economics from Virginia Tech and a JD from the University of Tennessee Law School. He has completed his postgraduate work in business administration and educational counseling. Zane is a member of the American Society of Training and Development and the International Association of Hostage Negotiators. Before Zane gets started, I have just a few housekeeping items. We will be answering questions today at the end of the webinar. Please send your questions in as soon as you think of them through the question tab on the webinar control panel. Zane will answer as many questions as he can today, but if we do not get to your question, we will reach out to you after the webinar. The webinar is being recorded today, so if you experience connection problems during the live presentation, a recording will be available by request within 24 hours of the live version, and it will also be posted on our webinar archive, which is located on our website. I will send the link out on our chat window just so that you can have it. I'm now going to turn the presentation over to Zane. Welcome and thank you for joining us.
And happy lunchtime. I appreciate your taking your lunchtime to be with us today. This should be an interesting webinar. It basically springs out of a request that we get a lot to evaluate and tell people exactly what is my return if I invest in Core or Genesis or doing the MBSE process using those tools more accurately. And that's a good frame for that question because it is an investment. Very often we look at expenditures for tools and methods as a cost, as an expense. And that's really not the way to look at it. And I think you'll see that as we cover the subject today, that it is an investment, and it's an investment that pays you back the further you go. So it's not just simply an upfront cost. There is an upfront cost, but that cost is an investment. So people want to know, what's the return on that investment? If I'm going to make it today, what can I expect as my return? So we tasked one of our engineers to write a paper on that subject. He did some research, looked at experiences, his own experiences and the experiences of others, and came up with some projections with respect to the return on investment for Core. Now, although the paper addresses Core specifically, and we'll talk about Core specifically, the same kinds of return are available with Genesis as well, which is our .NET product. Very often we give webinars where the topic is more academic, where we don't engage really in advocacy for our methods or our particular tools, but we talk about, take a more academic tack in talking about systems engineering subjects. That's not the case today. I'm going to be an unabashed advocate for our particular methods and tools, and I'm going to talk about the specific return for making the decision to invest. So let's get started. What we're going to do is we're going to show you how you get back at least $2.54 for every dollar you invest in this way. And you'll see how we derive that number. We're going to talk first about the assumptions that we made in going through this analysis. Then we'll move to an example configuration because specific numbers vary from configuration to configuration. So in our assumptions, we assumed everything conservatively. So we tried to err on the side of a conservative estimate of what your return would be. And then we assumed an example that's fairly robust. It's not trivial, and it's not over the top. So it's a good, robust example to consider as we look at the return on investment. I'll give you an overview of the actual calculation of the return on investment at a very high level, how we derived it, and then we'll drill down into 3 direct savings examples that show you how we came to those numbers. We'll talk some about additional returns on our investment, and then we'll talk a little bit about how it's done. How does CORE produce that? And much of that is the same for Genesis as well. And we'll wrap it up with conclusions. That said, let's get started. Our basic general assumption is that our calculations are based on the most conservative values for any particular value that we're looking at. So where we have chosen to err, where you don't have a lot of specificity, we have tried to err on the side of a higher cost, in other words, a larger investment, and err on the side of a smaller return. And you'll see that manifested as we go through the presentation. You'll see how that conservative estimating comes across. We have also assumed that we're talking about the standard system development phases. We're all familiar with these. We begin, we're doing a top-down project here as an example. So we begin with defining the user needs and system operations. Then from there we create a system specification. We develop system architecture and specify the subsystems. We move through designing the subsystems and assemblies, and then implement those into a larger system, and finally integrate and test the system and subsystems. All of that we're familiar with as a concept to production kind of a design process. We also consider program management and technical publications issues that we all find are a part of every project that we do, but are not tied to any specific phase. So we may have those from the beginning up to the final reports and the program management completely across the life cycle. So this last category is here. We have assumed that all these are present in our example. So let's talk about our example project configuration. We are making assumptions about a particular product to use as an example because we have to have a way to tie it down. But we've tried to be, as I said, conservative, and we've tried to make assumptions that don't invalidate the calculations. So you don't come away with an ROI that's specifically tied to a particular example. We're using the example not to determine the ROI, but we're using the example to be able to talk about how we get there. So our example project investment involves 3 core named clients, 3 editions of core tied to particular workstations or computers, 2 core floating clients that can move around, a core server to enable collaboration and pull all of it together, 5 core to net users who are accessing the information through the net and intranet typically. And then we are assuming that you're going to take MBSE core training for the 9 users that are going to be involved. You're going to engage us for some project setup and mentoring with coaching as a beginning piece of your project to get you started on the right foot for your first project. And we're going to assume that we take core scripting training, which will enable us to do some of the things that we'll talk about later. So that's our initial configuration. Our example product setup costs are to set up the documentation generation, and we'll talk about specifically what that is. We're including that as an upfront cost, but when we talk about, for instance, auto generation of documents, you're going to see that come up again. Part of our conservative approach is we've tied that one-time cost into that particular element of the return, so that reduces some of your return there. But we've also put it up front, so it's a part of the upfront calculation as well. The cost to develop reusable subsystems is included here as an upfront cost. That involves setting up a reuse library and getting your designs configured for that. So we've included that as a part of the upfront cost, and an opportunity cost for the team to set up and become familiar with core. There is some learning curve, and you want to get it set up, you want to get it set up right, and you want to become familiar with it as you enter into your design. So we have used that as a part of the initial setup cost. So you have the deployment cost, which is the cost of your software and your training up front, and then you have your one-time configuration setups. The deployment cost was pulled off the price list at the time of the writing of the paper and was $121,000 at that point, and then the one-time configuration and setup costs were $81,200. So you have a total investment of $202,200, and that's our project example to give you a size and to give you your initial investment. So now let's begin to talk about the return on that investment and how we've calculated what the return is. I'll begin at a high level and show you what the return is at a high level, and then we'll drill down into some of the specifics. What was done in the writing of this paper was that we took experience with projects, with some specific projects and some general experience, and went through the particular project phases and made some calculations about how much would be saved or not saved, as the case may be, in each one of those phases. That's discussed in detail in the paper, and so you'll be getting a link to the paper after the webinar, and if you're interested, you can drill into that and see how those calculations were made. But on the front end, defining the user needs and the system operation, the two columns are without core on the left and with core on the right. So that's pretty much the same in terms of your labor hours that you're going to use for that, either way you go, as is specifying the system. In the very beginning of the project, you're really not working in core. You're coming up with your specifications and ConOps, etc. So those two costs are the same for either one. When you get into developing the system architecture and specifying the subsystems, however, you begin to get into a difference. Doing it without core, without the tool to leverage, versus doing it with the tool, and you see you begin to save some hours here. In designing subsystems and assemblies, as you move from the high level to increase the granularity and drill down into your design, you begin to experience additional savings, and how those savings come about are detailed, as I said, in the paper. Implementing the subsystems and assemblies is the same story. So again, you're experiencing some substantial savings. Integrating and testing subsystems and then the systems, once again, you save on that because of the way it's done physically without the tool and the way that it's done virtually with the tool. And then you have what we talked about as phase independent cost savings that result from using CORE. So CORE will leverage your program management, and we'll talk about that in some detail. And then the TechPubs area that we have all struggled with becomes a very significant piece of what using Core Genesis brings to the table, because you're able to automate that. And at the end of the webinar, we'll talk about how that comes to pass. So the total savings in terms of labor hours is $59.64. We've assumed a blended labor rate, a burdened rate, at $120 per hour on the engineering costs here, and so the total savings, $59.64 at $120 an hour, is $715,697. Now, when you begin to calculate the return on investment, what you want to do is you want to look at your savings against your cost and express that as a ratio with the cost in the denominator. So you take your savings and subtract out of that what you had to make as an upfront investment, and then divide that by your investment, and you find out pretty quickly that you get $2.54 for every dollar you invest in adopting this solution. So let's drill into that in some detail and take a look at what we're talking about and how we make these statements. So we're going to consider 3 examples, and we're going to begin by building those examples into a cost structure with a total on them. So the 3 examples are going to be a single-use structure, and we're going to assume that there's one subsystem here that we're going to use again, and in the old school way, what we do is every time we reuse it, we design it again, in essence. There's some small savings from having done the thought process, but the manual labor of doing the design work is essentially the same. So if you use the structure over again, then you're going to have an additional cost. That we found, and the paper discusses how that came to be, as $240,000 for that particular single-use redesign work. The next item that we're going to consider is the generation of documents, and we have tracked, we're assuming 7 different types of documents that need to be produced over the course of the project, and those will wind up being produced at a cost of $143,100. And then finally, we have the cost of correcting defects. As you correct the defects in your project, in your system, you have to go back and fix them. And we'll talk about what it will mean to detect those earlier and get them fixed before they become really expensive. So we have our total cost structure here with just these 3 items, these 3 components of the return on investment of $467,310. So how are we going to make reductions to that? Well, let's consider the single use versus reuse and begin here. The advantage that you get is that you can develop a library of reusable subsystems or assemblies that you know you're going to use over and over again. You can leverage this library in the same project, which is what we're doing in this particular example, or you could maintain it and use it again and again in different projects. So you might be using this over and over again in successive projects. You will experience the savings that we talk about every time you engage in the reuse. This will translate across to re-experiencing those savings every time you take advantage of the reuse library. The systems are stored with the complete interface definitions, so they are essentially ready to be tweaked if they need to be tweaked, but they're ready to plug in as they are. So they're there in the library ready for you to reuse. Now in our example, we used historical data that was gathered from actual design experience. And the actual design experience showed us that 2 out of the 5 subsystems in question in the reference projects wind up getting reused. But we found that the design reuse reduced the specification and implementation time and cost for each subsystem reuse by 71.5%. Well, what does that translate out to be? What does that look like? Well, the old school example, and what we've assumed that we're going to reuse a single subsystem. So we got one of our subsystems and we're going to use it twice in our project. We're assuming that it's a complex subsystem with 100 interfaces. So that's gonna be a significant undertaking. The redesign is going to require 2 engineers 6 months work. And the engineering rate, the burden rate, is assumed to be $120 an hour. So 6 months work is 1,000 hours per engineer. We've got 2 engineers, so we have 2,000 hours at $120 an hour is $240,000 to do a redesign of this system. Well, what would be the impact of reusing the first design in the second instance? Well, once again, we're assuming a single subsystem reuse, the same complex 100 interface system. The redesign requires leveraging the system in the library. So the burden rate is the same, of course, at $120 an hour. And here you see how we wind up including this twice in the name of being conservative with it here. So although your $202,200 initial investment includes the time to set up the reuse library, we're going to assume that it took us 58 hours to set up the reuse library for use here in this project. And then adapting the subsystem for the new use, of course, you're not just going to plug things straight in with no investment, but it's 512 hours instead of the 2,000 hours that we saw before. So in this instance, we wind up with $68,400. So what are our savings from our reuse versus the old school way? Well, the old school way, it costs $240,000, but with the reuse it costs $68,400. So we have a savings of $171,600. Now, keep in mind that we have a single reuse assumed in this project. You're going to experience that savings over and over and over again. And actually, there'll be more savings than that because setting up your reuse library only needs to be done once. So that cost actually could be allocated out across all of the reuse that you use. But per reuse, you're saving $171,600. So you can see we're beginning to develop the green as we're going to track our total savings. So we've dropped our total cost down by the $171,600 figure. Now our next example is automating documents. Now the thing that I haven't included here, and anybody who's ever done this will know exactly what I mean, I have not quantified, and the paper does not quantify, the frustration factor. Producing these documents has a huge hassle factor with it in addition to just the raw work. but we're going to look at the manual generation of 7 different types of documents across the project and see what we can save there. So documentation, CORE uses a single database and a single repository for all the entities and relationships that we define as we do the design. So they're held there, and they're held in relationship. That means that documents, when they're produced, are the pre-formatted answers to defined queries of the database. So in other words, if you're doing an SSDD, you simply launch that query to the database, and the database retrieves the information that's specified in that query and puts it into the format that's specified into the query and returns that to you as a document. That's in contrast to the way of assembling the answer, of preparing a specific type of document and going in to all your different locations for data and assembling all that, and then trying to set all that into alignment, produce the information, and then format it and produce the one-off documents. CORE allows the user to simply submit the query instead of doing that. So you have the customization of both the query and the output are facilitated in the tool. So you can, in advance, customize both what information you want out of the database as well as what format you want it to be in when you produce it. Our example, the old school way, of course you don't have to set anything up. You've got the raw sources of the data laid out in front of you. So there's nothing here to configure. So you don't have any setup costs to do it this way. But your documentation costs are 1,908 hours, and that's broken down into the authoring cost of 516 hours, correcting the content 697, and the tech pub and writing costs of 695 hours. So you wind up with a total of 1,908. And what we've done here is we've dropped the rate. We've used a blended rate here, assuming that we're having some tech pubs people work and some engineering time. So we've, in an abundance of caution, and once again part of our conservative estimating here, we've dropped the hourly cost to $75 an hour instead of the pure $120 an hour. And so it costs $143,100 at that rate to produce your documentation. Now, when we do it in CORE, we have some upfront cost, and once again, this was already included in the 202,200 initial investment cost, but we're going to assume that we set up 7 types of documents, and we're going to do that essentially from scratch. Now in CORE you wouldn't be doing it from scratch. CORE comes with a robust set of documents that are already set up. In other words, the desired information is specified for the query, and the desired output is specified, and all you would have to do would be tweak it. But we here assumed that you did it essentially from scratch. We've assumed that you're going to pay $8,000 to take the scripting class so that your engineers who produce the documents know how to do the scripting that specifies what information and what format. And your document production time becomes 387 hours. We're again using the blended rate of $75 an hour, and so you have a one-time cost of $8,000 from the class plus 560 hours at $75 an hour, and that's $50,000 in the one time. Then you come back and the document production costs you 387 hours at $75 an hour, or another $29,075, so you have a total of $79,075. Now when we go back and compare that with the old school way of doing it, manually generating your documents, you see that you wind up with a savings of $64,025. Now, notice that this percentage of savings, this is a 79% savings on your document production costs. So if you were to ignore the setup cost, because once you've made the initial setup, you've made that, the ongoing savings of 79% of your document production costs would be re-experienced all across. Every time you produced a document, you would re-experience that savings. So you can see here now we make another drop and our total savings is $235,625, and we move to the next area for savings, which is the area of defect detection. Now, we know from experience, and most of us have had the opportunity to learn this the hard way, that your cost of fixing defects in your design rises as you move through from analysis to design to implementation, integration, and fielding. As you move through the phases of the life cycle of your design project, that cost is going to go up and go up dramatically. So it climbs depending on where you take it. The advantage that you're going to have with CORE, with this single repository, single database, single and one model of your design, is that you are going to get the ability to detect your design flaws early. You're going to detect your defects. Most of your defects, one way or another, come out to be inconsistent designs or incomplete designs. So you wind up with omissions. Design omissions create most of your defects. For example, you'll have requirements, but you don't have any test case for the requirements. Or you'll have requirements that are not implemented. They're not tied to functions, and therefore not allocated into the architecture through the functions. You'll have dangling or unconnected interfaces, things that just simply don't connect up. Missing design descriptions, pieces of information that you're going to need that are not specified in your design, and architectural elements that perform no functions. So aspects of your physical implementation that are really not called for in your functional analysis, and therefore probably not called for in your requirements either. When you're using an automated tool like this, with the capability that CORE has, CORE produces reports and tells you where these things are. So for instance, this is a Word document spit directly out of CORE, reporting the results of consistency and completeness checks that show where you have potential design defects. Where does this come out? Where does this come to light? It comes to light at the point that you're running the report. So throughout the early stages of this design, you'll rerun this report and discover any design omissions up front. Now, we made some assumptions about what we're going to find. You have software and hardware defects. And we think in most of the projects that we deal with, we find that the software defects run about 2 to 1 over the hardware defects. And we find that 75% of the defects are created by design omissions. So based on the research that went into the paper, those were 2 assumptions that we made. Now, when we look at it with respect to the cost of correcting the defects with software defects, which comes out to be, we assumed, for example, 100 defects, so 67 of them are going to be software defects. The first component of your cost is the labor hours to run the core diagnostics. Well, you're not running core diagnostics without core, but with core, that's 8 83 thousandths of an hour, labor hour, to run that. All you have to do is ask for the report. The labor hours to diagnose a failed test, it's not applicable in core because you're just running the diagnostic, but it would be a half an hour in the traditional way. The labor hours to change the labor hours to assess the change required to fix the system is the same for both. Once you know the defect, your analysis is the same. The engineering labor hours on hardware are not applicable in this analysis. Engineering labor hours on the software to fix the system, 2 hours the old school way, but it's not applicable with core discovering it in this way. Labor hours on software to unit test the software fix is an hour in the old school way, but not applicable with core. And then neither of the next two are hardware issues, so they're not applicable here. We used an average hourly burden rate, and this was the number of defects. So with the hardware, you run the same kind of analysis, and you see that there are some savings that results in the discovery of hardware with core and without core. So you have the same kinds of savings analysis. So looking at old school winds up calculating out to $84,210, and this is detailed in the paper. And the analysis with core is $44,299. So you got an additional $39,911 in savings. So we find now that out of the total of $467,310 for these three cost components, we have, through the use of core, saved $275,835 just on these components. That gives you an idea of how we've done the analysis and what's there. The detailed nitty-gritty aspects of this analysis are fully reported in the paper, and we'll be giving you a link to that, and I certainly want to encourage you to read that. So we've driven down the initial 467,310 down to 191,475. That's a substantial savings in anybody's book, and a component of the return on investment here. But there are additional kinds of return that are not as easily quantified, but certainly something that we want to keep track of. So let's look first at project management. If you look at project management, it boils down to concerns in about 10 different areas. So the project manager is going to be concerned with these 10 different areas. When we look at Core and Genesis, we find that we get help in these areas. The first is the area of integration. Core has an integration schema, and you see the output from a particular project schema there in the display. Certainly, your scope is managed through your requirements, and you have direct hands-on requirements management capability through the tool. Time and scope are going to be managed through your WBS, and Core is capable of producing WBS with cost roll-ups, so you have additional help there. You need real-time metrics for your project management, and Core can spit out those real-time metrics, which are obtained from the project design and essentially structured by the engineer or the program manager and produced as needed. Communications is enhanced even to the point of providing HTML output so that other people who are not hands-on in the tool but need to look at the design and have information about the design can access it that way. Core has risk rating capability, so you can influence the risk management. So you can see that Core gives the program management aspects of the project a significant boost up. Another area is an area that we like to call virtual prototyping. When you engage in MBSE through the use of Core, and we teach this methodology in our class, we begin at a very high level and we work in all 4 domains at a very high level, or actually a low level of granularity. So we're taking a high level look at the project, at the design, with pretty low granularity. But as we drop the levels, as we drill down into the design and increase the granularity, we stay complete in all 4 domains, which means that you wind up with an executable design, an executable model, and an executable logical model at every level, because you stay complete in all 4 domains. You don't stovepipe, you don't lose things, you don't have to put things together, retrieving them out of separate tools or from separate repositories, but you're complete, your design is complete in all 4 domains at every stage along the way. Core simulation capability allows logical simulation with relevant conditions, so you can impose conditions on it. You can simulate using statistical conditions that are imposed. You can run what some of us have called Monte Carlo light with repetitive simulations. There is no additional cost to generate a prototype and export it out for simulation for the logical model. And then finally, the virtual prototype has a marginal cost of nothing. It's there available all the time because your design is complete all the time. So you simply test the design itself. You don't have to produce a separate prototype, package it up, and send it out for simulation. So you're able to prototype at every stage. And finally, probably the most important thing and the hardest piece of this to quantify is the increase in the quality. The early detection of defects, the reuse, the completeness and consistency checks, all of those things contribute to a higher quality solution. So you have a complete and consistent model at every level of granularity as you move through your design, and that leads to higher quality. You're able to wrangle complexity because you're not having to ferret complexity out from a bunch of different sources. You're holding everything in relationship in the model. And out of this kind of logical model, you get discipline, insight, and communication. Everybody's aligned. The model is there in front of you. You can discuss it. You can modify it. It's all consistent. When you make modifications to it, they're made in the model, not just in a particular representation. So you're able to gain insight. You're able to communicate, and the consistency and completeness provide a discipline that comes from the tool and does not have to be imposed manually, so to speak. So how can Core do this? How does this happen? Well, it mostly centers on not on the bells and whistles, but on the power of the repository. If you take a typical design effort, what you wind up with is different aspects of the design lodged in different representations. So I have a requirements tool, and I can spit out information out of the requirements tool, and that gives me information about my requirements, but none of those requirements are hooked to functions because that particular way of looking at it doesn't include any kind of functional analysis or link up. So you wind up with a highly compartmentalized model of this solution that you're trying to produce. And all of the representations and all of the information is walled off from each other. Now, we tend to make that worse by using tools that create walls between the tools. So not only are there walls between particular representations, but you wind up with walls between the tools. So you don't have functional analysis capability in a requirements tool, or you don't have physical architecture capability along with functional analysis, or maybe you bridge two of those together but you don't have a third one, or you can't do verification and validation, and so you find that you're porting information back and forth, and it's compartmentalized. Many of the tools that you'll find lodge the information about the model with a particular view. So that information is not shared across to another view. So you have a view that may be packed with some information, but that's discrete from another view. So you have divisions between domains, you have divisions between the views themselves, you have divisions among the tools, and you have, you wind up with people advocating separate models. We have to have a requirements model and a behavioral model and an architectural model, and so we find people advocating. CORE puts all of those together, and I find it humorous when I go somewhere and I hear a presentation, somebody asks a question about that, and the presenter who's advocating something different says, well, it's not possible to do that. Really. I know that it is possible because we are doing that. That's the whole point of what we're doing. So what we're trying to do is to utilize the power of the repository, the power of the database, and put an end to the fragmentation and an end to the walling off of the different domains and tools and visualizations. How does that work? Well, the way it works is you use a single model, and the model includes all of the entities, their attributes, and all of the relationships in their attributes. So you have a model that's all webbed together with the entities, whether the entity is a requirement or a function or a component. All of those entities are there. A data store, a trigger, whatever your entities are, they're all there, and they're all in relationship. The tool disciplines you to make sure that you have all of the relationships established, and you can see that. You can turn it around and turn it over and see all of that fully in relationship. This integration is powerful. It's powerful because it gives you insight into the entire solution, not just to one particular aspect of the solution. And it doesn't ask you to take limited chunks of insight and try to wedge them together. So how does this come out to help us practically? Well, the first power of the repository can be looked at from the input side of the equation. If you're going to make inputs into different views and different tools with a fragmented storage space, you're called upon to make a particular change and make it not just in one view, but you've got to figure out where are all the other places that it will show up, and you are responsible for moving around to all those places and making those changes in all the places. In other words, you become the repository. There's nobody out there who's not using a single repository. The question is, where is the repository? I find it humorous when people talk about, model-based systems engineering. There's no such thing as systems engineering that's not model-based. We all have a model. The issue is, do we have a model that's managed and contained in a tool, or do we have a model that we're trying to maintain in our heads? So on the input side, if we don't have a fully integrated model, then we're responsible for doing the integration ourselves. It's different with core. Why? Because when we make a change through whatever interface, through a particular view or through the property sheets or however we decide to make that, that's put into the model in relationship. And in fact, if you try to put it into the model and you don't have the relationships complete, the model asks you, where are they? So the tool is managing all of that, and you're able to make your changes, and you don't have to worry. In fact, if you make a change in a sequence diagram and say add a function to a sequence diagram in core, and now you want to look at an activity diagram, when you open the activity diagram, the new function is already there. Why? Because the function's really being added in the model. It's not, it looks like it's being added to the view, and it is, but it's being added and then managed in the model. So it helps you on the input side because it makes the tool the manager instead of us the manager with our brain power. On the output side, if you're doing output the old school way, then you have to query all the places that house the information that you want and put all that together as a package of information, assemble it, and then pass it over and then configure it and produce it. So you have all of those tasks to be done, and that's the case that we went through with manual versus automated documentation production. But you have a number of queries made to a number of different places, and hopefully you've made all the queries and you've made them in all the right places, and you've packaged all that information. It's assembled correctly and then produced correctly. When you do it in core, it looks like this. You're sending one standard query to the model. The model gathers the information, the core gathers the information from the model, rather, and passes it back out to you. Your query has already specified what your output's going to look like, so you just simply print it out. It's pretty much that simple. So it helps you on the input side and on the output side. Core uses the power of its single model, single repository to integrate the design and to keep it integrated for us. That results in significant savings, but it also results in an increase in quality. You can have a higher confidence in your solution, and your solution is a higher quality solution. We have, and I think you've seen as we went through some of the calculations, conservatively speaking, we have done a conservative analysis and seen that that results in an ROI of $2.54 return for every dollar invested in the core solution. Could we be off a few pennies? Yeah, you're probably off a few pennies. But you are more probably off by being too low a return on investment than being too high in the return on investment because of the conservative way that we approached it and because of the high quality research that went into this. So to sum up, if you invest $1, you get $2.54 back. It is an investment. It's an investment not just in today's project, today's design, today's solution, but it's an investment in the projects going forward. It's a change in the way of thinking. it's a significant paradigm shift. You can see how by reading the paper. As I said, we'll be publicizing the link to you so that you can download the paper and take a look at it in more detail. But this has been a fairly high-level overview, and I hope it's been useful and enjoyable. And now we're ready for questions.
All right, thank you so much, Zane. If you do need to step out of the webinar now, I do ask that you at least take a few moments to fill out the quick survey that will pop up on your screen, but we do have a few questions to go through. The first is actually more of a comment from Stephen, and he says, when creating documents manually, the documents are often very inconsistent as you take a document from another project and you hack at it to fit the new document. There's lots of errors doing this method, and he wanted to point out that that is definitely part of that frustration factor. So I just wanted to share that. Let him know that we all know that feeling.
Yeah, I'm with you on that one, Steve.
All right, and so the first actual question I have is from Mark, and he asks, would $75 an hour really be a good basis for core-based document production? This would assume that the tech writers have and know core, would it not? And are tech writers even needed for this core scenario?
It depends on the size of the project in terms of physical production. You write the script one time, so that's engineering time. Running the script and getting the output and collating things together and duplication, all of those kinds of things wind up consuming some tech pub time in the same way that the manual production of documents consumes tech pub time on the very tail end of it once the document itself is right. But on the front end, you're looking at folks who have taken the scripting class and they do that one-time customization. So we've deliberately tried to overestimate the amount of time there, so to drive up the core cost.
Okay, thank you. The next one is from John. He asks, is data passed and parsed between domains like modeling tools, or for example, passing propulsion data that is used in trajectories, or electrical data shared or used in various systems?
The data is available to come out of the tools. If you're talking about building the logical model and the model of the architecture, then yes, the data is there available and can be used wherever it's relevant. If you're talking about a physics-based model, for instance, then you would be passing data out of the tool to the physics-based modeling function, or passing information from the physics-based model back into the tool. But within the tool, within the logical simulation, and within the design of the different domains, the data is available across all the domains.
Okay, great, thank you. And I do have one more. It's from Lori, and she asks, she says that core does not provide analytical results after simulations run automatically, so the engineer must spend additional time making sense of the runs, and that is an extra cost that must be accounted for. So I think she's looking for how that was integrated into the design of the paper.
Actually, it depends on what you mean by analytical costs. It actually does report, gives you a log and reports what happened. So you do have the information that flows out of the simulation there. I'm not sure if that's what she's driving at, but that is produced as a part of running the simulation. In fact, there's a window for it down at the bottom of the simulator that produces a report as it's run.
Okay, great. Thank you. Lori, if you've got additional questions and you're still there, feel free to send them in, or you can get the questions to Zane, and I'm sure he'll be happy to help you out. That does wrap up our final Q&A for today's presentation. If you have any other questions or comments for Zane, please don't hesitate to shoot him an email. You can see his email address on your screen now, or you can post your questions and comments in the forum of our community site at community.vitechcorp.com, and I will send out the link. We also, if you prefer, we are active on LinkedIn. You can search Vitech Corporation there, and we have a group you can join and participate in that. And for our next webinar, if you're involved in Vitech's university program using Core in the Classroom, you'll be receiving an invitation next week for our webinar scheduled on December 16th. Customer Care Specialist Bethany Maddox and I will be co-presenting on ways to maximize the student experience with Core 9. If you are not involved in the university program but feel like it's something that might be something you'd be interested in, please visit the link that I'm sending out via the chat window now. You can also stay up to date on all of our upcoming webinars by visiting our webinar calendar online, and again, that will also be chatted out to the group. And we have one more note as a reminder is as you log out of the webinar today, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you'd like to see covered in future webinars. So let me get you those two links and our webinar calendar. And thank you so much to everybody, and we look forward to seeing you again in a future webinar. Have a wonderful day.
Thank you.